Welcome back, students. Today we will learn about graphs. Now, a computer network or an internet is considered is arranged as a graph. We can consider this as a collection of nodes and edges. So here every system that is connected over the network is considered as a node, and the connection link that is established is an edge here. So this diagram depicts computer networks as a graph. With the application of graph, we can consider it as traveling salesman problem. So here we begin with a node. That is the starting node, and we traverse some intermediate node, finding the shortest path that collects all cities without a loop here. Now let us try to understand the concept of graphs. A graph G is a collection of vertices and edges. Vertices are also called as nodes. So these are the nodes, and when edges is a link between two nodes, and it has got some weight. So a graph G composed of V and E, whereas V is the set of vertices or nodes and E is the set of edges, that is arcs connecting the vertices in V. An edge is equal to U comma V, which is a pair of vertices. So an edge always connects the two vertices. So it will have a pair of vertices. We'll call it as an edge. So here on the slide you can see an example where we are having 5 nodes labeled as A, B, C, D and E. So V consists of all of these vertices, that is nodes. You can see V is equals to A, B, C, D, E, whereas E composed of an edge connecting A and C, A and B, A and D, D and C, and so on. So here is a pair. So an edge always represents a pair of vertices. Now there are two types of graphs: directed graph and undirected graph. Directed graph always has an edge oriented vertex. It means that it always have a direction over the edge pointing outward to the node, whereas undirected graph shows only the connection. There is no orientation, no direction is shown. Now there are some concepts related to graph. Let us see what are these. First is degree of a vertex. The degree of a vertex is the number of edges to that vertex. So if you want to calculate the degree of a vertex, you need to calculate the number of edges over that vertex. Now in case of a directed graph, the in degree of a vertex V is the number of edges that have V as the head. It means that whatever vertex you are considering here, you need to calculate the number of edges that are heading towards this particular vertex V. Okay, this will give you in degree of that vertex. Out degree of a vertex can be calculated as the number of edges that have V as the tail. That means here you need to calculate the number of edges that are going out from this particular vertex V. So now here vertex V becomes the tail. If di is the degree of a vertex I in a graph G with n vertices and e edges, the number of edges can be calculated by the given formula as E is equals to summation over 0 to n minus 1 di divided by 2. So here di will give you the degree of the ith vertex. If you want to calculate the number of edges for this vertex, you need to first calculate the degree of that vertex and place it into the formula, and you will get the number of edges. So as a hint, you can use here adjacent vertices, which are counted here twice. I hope you understood this concept. Now let us see what is subgraph. Now a graph, we have now a better understanding about it. Whereas a subgraph is a subset of vertices and edges. See here, this figure gives you a better understanding. We have a graph that is having 4 vertices, and here we have 5 edges. Now if this is the graph G, a subgraph can be formed out of this G by reducing the number of edges as well as vertices. So a subgraph will not include all of the vertices and all of the edges into it, but it will include a subset, a small number of vertices and edges will be included in the subgraph. Here you can see. Now the next concept related to graph is a path. Now a simple path is a path that such that all vertices are distinct, except that the first and the last could be the same. A simple path, if you want to know about a simple path, it is actually a path that you are taking from one vertex to another vertex, traveling by the edges, but those are distinct. So you are traveling from one node to another node, forming a path, but the the vertices that come in along the path, they are distinct, they are different. Okay, hence it forms a path here. Now the first and the last vertex can be seen. If so, you have a closed graph. So a simple path here in this figure, we can say A, B, C, D is a simple path. The next concept is cycle. Cycle, you can imagine a cycle as a loop where the path starts and ends at the same point. So just now we have calculated path in the figure. So ABCD was a path. A path is different from a cycle. So the difference is that you are taking the same path, but the starting and ending node or vertex is the same node here. So it forms a cycle. It is forming a loop here. See, in this case, if we begin at vertex C and we travel through B, D, and then we come back again to the same node C, it forms a cycle. Okay. For unidirected graph, the edges are distinct. For unidirected graph, the edges will be different, except for the first and last. The first and last node will be the same in case of a cycle. Now, another type of graph is connected and unconnected graph. So here we have the figure on the slide. You can see, in case of a connected graph, all of the nodes are connected via an edge. So this is a connected graph. Whereas in case of unconnected graph, you can see all of the nodes are present in the graph but they are not connected. See here, this particular node doesn't have any edge towards other node. So this is an example of unconnected graph. We have another type of graph, that is directed acyclic graph. Now the difference between a general graph and a directed acyclic graph is that this is a type of directed graph without any cycle. So here you will be having an edge pointing out towards, it will be showing you the orientation. That means from one node to another node, which path you can take, right? Showing the direction in which you can travel here. But in this graph, you will not find a cycle. That means first and last node will be the different. First and last vertex will not be the same here. Then we have weighted graph. Next type of graph is weighted and unweighted graph. Let us see what do we mean by weighted graph. A weighted graph is a graph with numbers assigned to its edges. Numbers assigned to its edges. As you can see, here we have an example. We have node 0, 1, 2, 3, and we have connecting edges to these nodes which are labeled some weight, which are having some weight assigned to it. Now this weight can be either the cost, that the cost we will be taking in case if we take this edge, in which we will take this edge to travel to other node, or it can be a distance, or it can be a travel time or hop, etc. So these are assigned some weight based on either distance, cost, travel time or hop. Now there are two types of representation of graphs. We can represent graph using adjacency matrix or adjacency list. We'll see it one by one. Adjacency matrix assumes n nodes in a graph. Now we are trying to generalize it using some notations here like n, m. Okay, we are not specifying the limit here to the number of nodes in a graph. So let us assume n is the number of nodes in a graph. So we use a matrix A ranging from 0 to n minus 1, and it is a two-dimensional matrix. Okay, if a vertex I and vertex j are adjacent in a graph, so in matrix showing the index number I and j, we will write there 1. Okay, so we are trying to build an adjacency matrix using the relations of the nodes in the graph, or the relations of the vertex in the graph. So if we see that the vertex I is adjacent to vertex j, or vertex j is adjacent to vertex I, then we will simply write 1. That means if they are adjacent to each other, we'll represent it as 1 in adjacency matrix. Otherwise we will represent it as 0. And we'll keep on building this adjacency matrix by considering each vertex in the graph. If vertex I has a loop, then also we will represent in adjacency matrix showing index I and I is equals to 1. If it doesn't have a loop means we are coming back to the same node from which we started. So if your graph is having a loop, then the value for adjacency matrix representing index number I, comma I will be 1. Otherwise it will be 0. Now to understand adjacency matrix, let us have an example. See, here we have a graph. Okay, so these are the nodes 0, 1, 2, 3, and we have connecting edges here. And now we try to build an adjacency matrix. So we'll just take the two indices as I and j. See here, to begin with the first node 0, if we have another node adjacent to it, now in this case we'll try to find if there exists an edge between 0 and 1 vertex. So vertex number 0 and vertex number 1, if they are having an edge between them, then we will simply represent it as 1. So see here, uh, you can see from vertex 0 to vertex 0. Okay, so this row and this column is 0 since it doesn't have a self loop. From vertex 0 to vertex 1 there exists an edge, so we simply wrote here 1. Let us see if there exists an edge between 0 to 2. Yes, so node 0, node 2 is having an edge, so we simply wrote here 1. Now find out if there exists an edge from node 0 to node 3. So there doesn't exist a direct edge. Okay, so we'll simply write here 0. Now moving towards the next node in the graph, that is node 1, we explore all the edges and represent it as 1 if there exists an edge to other node. So from node 1 we are having a connection to node 0 through an edge, so we wrote it as 1. From 1 to 1 there doesn't have any edge, so we represent it as 0. Then from node 1 to 2 we are having an edge, we write it as 1. Then from node 1 to 3 there also exists an edge, so we are writing it as 1, and so on. We'll try to explore all of these nodes in the graph, building up a adjacency matrix. So matrix A for this particular graph is given by this matrix. Okay, I hope you have understood how to build an adjacency matrix. Let us move to the next point. Now there are some distinguishing points between directed graph and undirected graph. If we see adjacency matrix and we are having undirected graph, then adjacency matrix is symmetric. That means whatever matrix we will be creating in undirected graph will be having the similar value here. See here, for a particular index into adjacency matrix as Aij is equal to Aji. Since it is not having any direction, so it is same. Whereas in case of directed graph, adjacency matrix is not similar, is not symmetric. See, A of ij is not equal to A of ji. Now we are trying to draw adjacency matrix for directed graph. Now just a simple thing we have done here. It is the same graph, but now it is having direction over the edge. So edge orientation is shown here. Now if we are having edge orientation, so adjacency matrix for this particular graph will be different, since we have to travel along the orientation of an edge. So from 0 to node 1, node 0 to node 1, we have a link. We have a link here. See, so in adjacency matrix there is no self loop, hence it is 0. Since we are having a directed edge over node 1 from node 0, so we'll write it as 1. From 0 again we are having an edge towards node 2, so we will write it as 1 again. And from 0 to 3 we are having an edge, so we'll write it as 1 again. Now look here, if we begin with the node 1, only one edge is there which is going outward, showing edge orientation towards node 3. So hence all other node is not having any oriented edge here. So we'll simply write it as 0, whereas towards node 3 we'll write it as 1. And from node 2, if we begin to find an outgoing edge, we'll find an outgoing edge to only node 3. So hence it will be represented as 1. Rest of the thing will be written as 0. Similar with the last node, node 3, since it doesn't have any edge outgoing towards another node, so all of the node connection will be represented as 0. So finally we got this adjacency matrix for this directed graph. We'll try to see how adjacency matrix can be formed using weighted graph. Now all of the edges are assigned some weight here, as you can see in this figure. So simply when there is a weight, we need to make the change in adjacency matrix. Earlier we used to write 1 if there exists a connection. If there exists a directed graph, we also represented it by 1. But now here if an edge is having a weight, so we'll simply write the same weight if there exists an edge between two nodes. So we'll replace it by the weight of that edge. See here, from 0 to 1 there is an edge having weight 10. So sorry, there is some mistake here. 0 to 1, see, 20 should be here and 10 should be here. Okay. And from 1 to, see, if you look by see, from 0 to 3 there exists an edge having weight 1, right? So here we wrote the edge weight in the adjacency matrix. Now moving ahead towards node 1, we explore all the edges to the adjacent node and write their weight in the adjacency matrix. So finally we got this adjacency matrix for this particular weighted graph. Let us see the second representation of graph, that is adjacency list. As the name indicates, it is a kind of a list. So an array of list, adjacency list is an array of list here. The ith element of the array is a list of vertices that connect to vertex I. See here, for every vertex we have a list. Okay, so from vertex 0, if there is a connection to other vertex, that is 1 in this case, we'll be having a node, right, pointing towards 1. So we can consider this as a linked list representation. So from vertex 0 that connects to vertex 1, then connects to vertex 2, and then finally connects to vertex 3. Since we do not have any other vertex from 3, its next pointer is null. Similarly, from vertex 1 we have a connection to vertex 3 and then null. From vertex 2 we have a connection to vertex 3 and no further connection here. From vertex 3 we do not have any outgoing edge, so it is not showing any pointer to other node. Simply we'll write it as null. Now in case of weighted graph, we can form an adjacency list using this. Now here in case of weighted graph, we'll have to represent the value. So here we'll be using we will be using a list, a linked list representation, which is having a value here, right? So from node 0 there exists a connection to node 1, and the weight for this particular edge is 10. So we simply wrote this. Now from 0 to next node is 2, having weight 20. So we wrote it like this. So simply we are just representing. In case if it is a weighted graph, you'll have to extend the node with an additional field, that is weight. I hope you got the concept. Now here we have a comparison of these representation in terms of cost, in terms of computational complexity. So in given two vertices u and v, we find out whether u and v are adjacent to each other. So what cost we are paying in case of adjacency matrix? So it is big O to 1. So this is the time complexity, computational complexity we can say in case of adjacency matrix. Whereas in case of adjacency list, it is the degree of node. So it is big O of n. N is the number of nodes. So given a vertex u, if we try to enumerate all the neighbors of u, the cost we are paying in case of adjacency matrix is On, whereas in case of adjacency list is the degree of the node. So it is similar to On again. Then for all vertices, if you are trying to find all the neighbors of each vertex, so the computational complexity is given by On square in case of adjacency matrix. Whereas in case of adjacency list, it is the summation of all nodes degree, that is OE. Now we have here complete graph. So in case of complete graph, there is an edge between any two vertices. Complete graph, we have an edge between any two vertices. So the total number of edges in a graph is calculated by this formula. E is equals to n into n minus 1 divided by 2. So here the time complexity is given by big On square in case of complete graph. So see, a complete graph is having a connection. From every node there is an edge to every other node in the graph. So if you are having 4 nodes, if you begin with any of the node in this graph, you'll find the connection to the all remaining nodes through an edge. This is called as a complete graph. A sparse graph is a graph where a small number of edges in the graph exist. A sparse graph is a graph where you have very small number of edges in the graph. See here, there will be a connection to the node. This is a connected graph only, but having less number of edges. So in this case we are having 4 nodes and there is a connection. They are connected, but not every node is connected to every other node in the graph. Okay, so the number of edges are less here. In this case you will find n minus 1 edges. If n is the number of nodes, there will be n minus 1 edges in the graph. And the complexity is given by ON. Now let us talk about the memory space requirement. In case of adjacency matrix, the space required is ON square, whereas adjacency list occupies OE memory space. In case of sparse graph, adjacency list gives you a better performance. If you are having a dense graph, then same running time will be required. Now graph traversal we'll see in the next lecture. That's it for today. We will meet in the next lecture. Till then, take care.